We've spent a lot of time in this course talking about several different types of numbers: whole numbers, integers, fractions, and decimals, to name a few. But it turns out that there are other very special numbers, very different kinds of numbers, which come up in mathematics, which we need to discuss in this lesson. So today I want to talk about one of these kinds of numbers, and they're known as the square roots. Now, as we begin this conversation, let's first talk about what square roots are. A square root is a number that you can multiply with itself to get a certain value. For example, the square root of 9 is 3, because 3 times 3 equals 9. And the square root of 100 is 10, because 10 times 10 equals 100. Now, I realize that 20 times 5 is also equal to 100, but 20 and 5 are not square roots because they are different numbers being multiplied together. Now, as you can see, the operation of taking the square root of a number is exactly the opposite operation of squaring a number, or raising the number to the power 2. In fact, the more technical phrase is that the operation of taking a square root is the inverse operation of squaring a number. And that means that it's going to be really helpful during this lesson to know several arithmetic facts that involve perfect squares, like the examples 5 squared equaling 25, or 6 squared equals 36, and 8 squared equals 64. In fact, I would suggest it would be a wonderful thing if you could memorize all the perfect squares up to about 15 times 15 equals 225. Now, let me share with you a more formal definition of the square root. For any real numbers a and b, if a squared equals b, then a is a square root of b. So, for example, since I know that 7 squared equals 49, I also know that the square root of 49 equals 7. And since I know that 8 squared equals 64, I also know that the square root of 64 equals 8. Do you see the inverse relationship here between squaring a number on the one hand and taking the square root of a number on the other? They basically undo one another in the examples that I just gave you. And in that sense, they're sort of like addition and subtraction being the inverses of one another, and multiplication and division being the inverses as well. Now, you may be thinking, why on earth would I want to take a square root? Well, square roots are used all the time in mathematics, so it's good to get comfortable with them right up front. And here are some simple examples of how square roots can solve problems in everyday life. Say you have a package of wildflower seeds, and it says that it will cover an area of 100 square feet, and you want to make a square patch of them in your garden. Well, if you take the square root of 100, then you'll see that each side of your square patch should be 10 feet long, and of course 10 feet wide because it's a square. And I know that it's 10 feet long and 10 feet wide because 10 is the square root of 100, or said another way, 10 times 10 equals 100. Or let's say that you have 64 members in your high school band, and you want to make a square formation in the middle of the football field at halftime with equal numbers of band members in each row and each column of the formation. Now, you could all scramble around the field till you figured it out, but you can also use some square roots. How many rows and columns should there be there for 64 band members? Well, if you said 8, which is the square root of 64, you'd already be thinking about square roots. And so in that case, you would want 8 rows with 8 people in each row, and you'd have your nice square formation. Well, as we walk through the rest of this lesson, I want us to learn how to do the arithmetic that involves square roots. You know, simplifying some square roots, applying the usual addition, subtraction, multiplication, and division when you have 2 square roots in the problem, and things like that. I've found in my years of teaching that many students struggle with square roots. So I want to make sure we cover as many examples as we can to try to help you avoid any kind of pitfalls that can occur. So let's now move to an example involving simplifying some square roots. Here's the example. The first one is pretty basic. I want us to simplify square root of 81. Now, as we walk through this example and the other examples in this lesson, we need to be able to think backwards pretty quickly. So here's the thinking that might go on. Do we know of any numbers which, when multiplied with themselves, give us 81 as an answer? Well, here's where those multiplication facts can come in handy if you've done those kinds of memorizations. If you think about it for a second, we know that 9 times 9 equals 81. And that means we know the answer to this example. The square root of 81 is 9, because 9 times 9, or 9 squared, equals 81. And so my answer here is simply 9. Now, sometimes these kinds of square root simplification problems don't work out to be nice whole numbers like we just got in the example we did. If the number under the square root symbol isn't a perfect square, then the answer will not simplify to a clean whole number. We can approximate it with a decimal number, like saying that the square root of 2 is approximately 1.414. But if we want an exact mathematical answer, we just leave the expression as a square root. So let's work on a few examples like that now, just to see what happens when the number under the square root symbol isn't a perfect square. Let's simplify square root of 18 as much as possible. Now, my first thought here is, oh no, 18 isn't a perfect square. So there must not be anything we can do to make this problem simpler. But that's not the right way to think about this problem. Let me suggest a different approach. Are there any numbers which divide 18 evenly which are perfect squares? For example, I know that 9 is a perfect square, and 9 goes into 18 evenly exactly 2 times. In other words, 9 is a divisor of 18. So that means I can think of the square root of 18 as the same as the square root of 9 times 2. Now, believe it or not, that's huge progress. And why is it huge progress? Because I can now use a very important property of square roots to help me. Here it is. When we have the square root of a product of two numbers, that is, the two numbers under the square root symbol are multiplied together, then it's the same as having the product of two different square roots. So what does that mean in this example? Well, it means that the square root of 18, which I can write as the square root of 9 times 2, is the same as the square root of 9 times the square root of 2. And notice how we just isolated that 9 into its own square root. I've written two separate square roots, if you will, and I've multiplied them back together. Now, that part that has the 9 by itself can be simplified because the square root of 9 equals 3. And therefore I know that the square root of 18, which is the same as the square root of 9 times 2, is the same as the square root of 9 times the square root of 2, which is equal to 3 times the square root of 2. Now, are we done? Well, to be honest with you, yes, we are. And the reason we know that we're done is because the number 2 that's under that square root symbol still doesn't have any perfect squares which divide into it evenly. Well, okay, it has a 1 that divides into it evenly, but that doesn't help us because the square root of 1 is just 1, and multiplying by a 1 doesn't do anything. So our final answer here really is 3 times the square root of 2. Now, before we leave this example, let me make one other comment about the notation here. When I write square root of 18 equals 3 times the square root of 2, we often are just going to write it as 3 right next to the square root of 2 symbol, and we're going to leave out the multiplication sign in between those two things. I'm going to do that from now on in this lesson. But keep in mind, when I write a number like the 3 right next to the square root of 2 symbol, what we're really saying is we want to take 3 times the square root of 2. There's a hidden multiplication there if you want to think of it that way. Okay, let's look at another example like the one that we just saw, and let's see if we can simplify. I want to simplify here the square root of 75, and I want to suggest that you try this one on your own first, and then we'll come together. Now, how do we start the process of simplifying square root of 75? Well, first of all, from the memorization that I've already done, I know that 75 is not a perfect square. So I can't quickly simplify this so that the answer is just a whole number. But the next best thing I can do is start to look for factors of 75 which are perfect squares. And I know the first few squares. They're 1, 4, 9, 16, 25, 36, and so on. Now here's the question. Do any of those numbers, except for the 1, divide 75 evenly? In other words, do they divide 75 with no remainder? And the answer is yes. Look at that 25 that is in the list of squares that I mentioned a moment ago. If I think about it for a second, I know that 75 equals 25 times 3. And again, notice how I had to think somewhat backwards there. I had to ask myself if 75 had any of these factors, and then I had to figure out what 25 times 3 in this case was in order to get to 75. Now that is a huge thing to notice, because it means that I can write the square root of 75 as square root of 25 times 3. Notice that the 25 and the 3 are both under the square root of symbol at that point. And now I can use the same property I used a moment ago and rewrite the square root of 25 times 3 as square root of 25 by itself times square root of 3. And now, from there, the square root of 25 can be simplified because the square root of 25 equals 5. And that means my final answer is 5 times the square root of 3. Now again, I'm not going to put that multiplication symbol in there, so you're just going to see a 5 right next to a square root of 3. But those two things are really being multiplied at that point. Now, notice that in the middle of that set of work, I used this fact that I could split a square root across the multiplication symbol. It's an immensely important fact when you're dealing with square roots. Also, notice sometimes I've said in this lesson that you have to know your basic multiplication facts in order to be able to do these problems. Here is a perfect example of this. Knowing those basic multiplication facts is going to be extremely helpful as we continue to simplify these square roots and work through these problems. Now, let me transition a bit to show you a few cousins to the problems that we just did. These are also important as you work with square roots. The first thing we can consider here is the problem of working in the opposite direction from what we were just doing, where we start with one square root and whittled it down to something simpler. Let me show you what I mean with the following example. I'd like to simplify square root of 14 times the square root of 7. So notice here that I've started the problem with two separate square roots already being multiplied together. Now, you might start by saying, look, is 14 a perfect square? No. Is 7 a perfect square? No. Okay, so we have to do something else other than simplifying those individual square roots. Okay, maybe one or the other number has a perfect square that divides it so that we could do the kinds of things we did in the earlier problems. But that's not true here either with 14 and 7. So what do? Do we just give up? Of course not. Since these two numbers are multiplied together, the square root of 14 times the square root of 7, I'm allowed to basically do the opposite of what I did in the other examples. Namely, I can rewrite square root of 14 times the square root of 7 as the square root of 14 times 7. Do you see how now the 14 times 7 is all under one large square root symbol? This is perfectly legal, and it's simply the opposite of what I did in those earlier examples. Multiplication is very friendly with square roots, and in this case, I was able to now put everything back under one square root thanks to the multiplication. Now, how does that help me? Well, notice that the square root of 14 times 7, which is what I'm working with now, is the same as the square root of 2 times 7 times 7, because 14 is 2 times 7. And of course, that can be rewritten as the square root of 2 times 49. 7 times 7 is 49. And do you know why that's nice? Well, because 49 is a perfect square. And so now I've reconstituted things under that square root symbol, and now I can do the splitting again. And I'm going to rewrite square root of 2 times 49 as square root of 2 times square root of 49. And that's nice because the square root of 49 is just 7. And so my answer really is square root of 2 times 7, which I'm going to rewrite as 7 times the square root of 2. So my final answer here is 7 times the square root of 2, or 7 square roots of 2, as some people like to say it. But notice how very different that final answer looks compared to the original problem. There was no 2 jumping out in the original statement of the problem, but here we get a pretty nice answer after we do all of that work with the multiplications. Now, let's look at a problem which is very similar to the problems we've already done, even though at first it doesn't appear to have any relationship with the earlier examples. Here is that problem. I want us to simplify square root of the fraction 36 over 25. Now, I can hear some of you say, hey, that's a fraction in there. We haven't done anything with fractions in this lesson. What in the world are we going to do? Well, it's true that there's a fraction inside that square root symbol, but it's not a problem. Why is it not a problem? Because just like multiplication, division and square roots are also very friendly. And that's because I can rewrite square root of the fraction 36 over 25 as square root of 36 over the square root of 25. Do you see how we split one square root into 2 square roots and gave ourselves a new fraction with an individual square root on top and an individual square root on the bottom? That's huge, and it's always allowed with division. And now things are very, very clean because the square root of 36 over 25, which is equal to the square root of 36 over the square root of 25, is just equal to 6 on top and divided by 5 on the bottom, because the square root of 36 equals 6 and the square root of 25 equals 5. And therefore, the thing we started with is simply the fraction 6 over 5. Okay, so square roots behave very nicely when we're dealing with multiplication and with division, as we've seen with the examples that we just worked through. What about addition and subtraction underneath a square root symbol? Well, the answer there is that in general, you cannot do much simplification with square roots that involve additions and subtractions. Let me be clear by looking at an example. Simplify square root of 4 plus 9. Now I want you to notice here that the 4 plus 9 is sitting all under one square root symbol. Now here I have that square root symbol and it's got an addition sign inside it. It's extremely tempting to write this thing as square root of 4 plus square root of 9. And one of the reasons that's tempting is because then it can be simplified to 2 plus 3. Square root of 4 is 2, square root of 9 is 3, and 2 plus 3 is 5. Unfortunately, that is completely wrong. Now, how do I know that? Well, if the answer is 5, then I must have been looking at the square root of 25, because square root of 25 equals 5. I'm not looking at the square root of 25. I'm looking at the square root of 13, because 4 plus 9 equals 13. So what's the problem? The problem is that in general, you cannot split the square root of a sum into the sum of 2 separate square roots. This is an error that I've seen hundreds of students make in my teaching career. Please do not fall into this trap. Don't split square roots across an addition symbol. It's wrong to do in almost every case, and so you should really, really avoid it. Now, by the way, subtraction also has this kind of problem. In general, square roots cannot be split across both addition symbols as well as subtraction symbols. They're just not friendly in those cases. Okay, now that makes decent sense, but what if I wanted to add or subtract 2 separate square roots? In other words, can anything be done if I'm doing something like square root of 5 plus square root of 5? Now notice that that is very different from the square root of 5 plus 5. If you're looking at square root of 5 plus square root of 5, you're looking at two separate square roots already. Well, it turns out that you can do something with the square root of 5 plus the square root of 5. The key is to think about like terms. In other words, square root of 5 and square root of 5 is like one banana and one banana. And of course, if you have one banana and one banana, then that gives you two bananas. Similarly, square root of 5 plus square root of 5 equals 2 times square root of 5, or 2 square roots of 5. Also, something like 3 times the square root of 7 plus 5 times the square root of 7, it equals 8 times the square root of 7, just like 3 bananas and 5 bananas would give you 8 bananas. But what if you were doing something a little bit different? What if you had 3 times the square root of 7 plus 4 times the square root of 5? Well, to be honest, you can't do anything to simplify that kind of an expression. Square root of 7 and square root of 5, they're both square roots, but they're very different square roots, so they can't be combined. Just like apples and oranges are both fruits, but not close enough to really say that you could combine them, unless I guess you make a fruit salad. But that's a different thing. Now, let's look at several examples of simplifying radical expressions that involve some addition and subtraction. Here's an example. Simplify 11 times the square root of 3 minus the square root of 12. Well, you might start off by saying, hey, square root of 3 and the square root of 12, they have different numbers under the square root symbols, so they aren't like terms, so there's nothing that I can do. You just told me that a moment ago. Well, you're correct when you say that 3 and 12 are very different numbers. But we should first see if their square roots can be simplified before we decide whether they have like terms or not. Watch this. Notice that the square root of 12 is equal to the square root of 4 times 3. 4 times 3 is 12. And we know that square roots are very friendly with multiplication, so I can take the square root of 4 times 3 and rewrite it as square root of 4 times the square root of 3. That's fine. And now the square root of 4 is just equal to 2, and so this all equals 2 times the square root of 3. That means that the original problem can be rewritten as 11 times the square root of 3 minus 2 times the square root of 3, because the square root of 12 equals 2 times the square root of 3. Aha! Notice now that we have like terms. Both terms have a square root of 3 in them. And I know that 11 minus 2 equals 9. So then 11 times the square root of 3 minus 2 times the square root of 3 has to equal 9 times the square root of 3. So notice here, when we started the problem, it didn't look like we could do anything. But it turned out with some little work in the middle, we could get to a nice final answer. Now, let's look at another example where we're doing this kind of simplification and the same kinds of things will arise. Let's simplify 17 times the square root of 5 minus 3 times the square root of 125 plus the square root of 100. Why don't you work on that one yourself for a moment, and then we'll come back together and make sure you got it right. Now, let's start by simplifying the square roots as much as we can before we move forward. That's usually a pretty good rule of thumb. Try to simplify them as much as you can before you try to do any adding or subtracting. Well, there's nothing to do with the square root of 5, so I'm going to leave that term alone for just a moment. Next, notice that the square root of 125 can be rewritten as the square root of 25 times 5. That sounds good. And now I can split that square root because it's got a multiplication underneath it. And that square root of 25 times 5, can be rewritten as square root of 25 times the square root of 5. And of course, the square root of 25 out in front there is just a 5. So all of that is equal to 5 times the square root of 5. So the second term can be rewritten as 3 times square root of 125 equals 3 times 5 times the square root of 5, which gives me 15 times the square root of 5, because 3 times 5 equals 15. Now, the third term is the square root of 100, which of course is just 10, and that doesn't have a square root of 5 left in it, but that's okay. I'm going to rewrite it as a 10 anyway. And that means that our original problem can be rewritten as follows. It started out as 17 times the square root of 5 minus 3 times the square root of 125 plus the square root of 100. That equals 17 times the square root of 5 minus 15 times the square root of 5 plus 10. And those first two terms have like terms because they both have a square root of 5 in them. 17 minus 15 equals 2. And so those first two terms combine to give me 2 times the square root of 5. And then, of course, I have to add the 10 at the end. That was there anyway. Now, notice that that 10 cannot be combined with the other term. Those two terms now are not like terms because the second term is missing a square root of 5. And so my final answer that I'm going to write here is 2 times the square root of 5 plus 10. Now, as we close this lesson, I'd like to take a few minutes to talk with you about the idea of finding the approximate value of a square root by hand rather than using a calculator. For example, it might be nice to know a good approximation to something like the square root of 30. If you punch that into a calculator, you would get an answer like 5.4772, and it would just keep going. But what if you wanted to get this by hand, at least accurate to maybe 2 or 3 places after the decimal point? Well, believe it or not, there are lots of ways to get such an estimate. One of the best known ways for doing that is something called Newton's method, which is named for Isaac Newton. But to be honest with you, that requires calculus to understand it. So I won't talk about that today. I should say, though, that Newton's method makes perfect sense once you've studied calculus. So that definitely gives you something to look forward to as you progress towards learning the calculus. Now, there's also a method for approximating square roots, which is known as the Babylonian method, and that predates Newton's method by several centuries, in fact. It's actually pretty straightforward and does not require any calculus whatsoever. But I'm not going to show you that one today in this lesson either. The method I want to show you is sometimes called the bisection method. Now, I'd like to demonstrate it to you by calculating an approximation for the square root of 30. First of all, I want you to notice that the square root of 30 has to live between 5 and 6 because 30 is between 25 and 36. The 25 is 5 squared and the 36 is 6 squared. So the square root of 30 has to be some number between 5 and 6. Now, once you've figured that out, you next take the number that's right between 5 and 6. And this is sometimes why people call this the bisection method, because we're bisecting that part of the number line between 5 and 6. Now, what is the number right between 5 and 6? It's 5.5. That's where the bisector would be. And now I'm going to ask myself this question. What is 5.5 squared? Because I'm taking this square root. Well, if we do some multiplication of decimal numbers that we learned several lessons ago, we're going to see that 5.5 squared is 30.25. And now that's pretty exciting because that number is close to 30. And that's what we were aiming for because we were calculating an approximation to the square root of 30. So we know that the square root of 30 must be close to 5.5. But 5.5 is just a bit too big because 5.5 squared is 30.25, and that overshot what I wanted. I just wanted 30. But now what we know is that the square root of 30 is between the 5 and the 5.5. Now that's better than knowing that it was between 5 and 6. We can now bisect that piece of the number line between 5 and 5.5 to see what we get then. When I bisect that piece, I'm going to go to 5.25. That's the number right between 5 and 5.5. So now I'm going to try 5.25 squared to see what I get. Well, that's just another multiplication of decimal numbers because it's 5.25 times 5.25. I know how to do that. And I can do it by hand and get 27.5625. Now that's smaller than 30. So now we know that we've squeezed square root of 30 between 5.25 and 5.5. We're closing in on this square root by doing this bisecting work. And now we find the midpoint between 5.25 and 5.5. That's 5.375. We square that number and we just keep going in this way. Eventually, we start to close in on the square root of 30. After another few steps like this, we will get to the square root of 30 being approximately 5.47. We knew it was just smaller than 5.5 when we saw that 5.5 squared was 30.25, and that was just a little bit more than 30. Now, of course, I can hear some of you say, wow, that was slow and it was tedious. It was a lot of work to do by hand. Well, I would agree with you with that sentiment to a certain extent. But at the same time, it's important that we understand what these kinds of algorithms or recipes are helping us to do. The Babylonian method and Newton's method actually get to a good approximation in much fewer steps than the bisection method. They're much more rapid about what we call convergence to a nice approximation. So those approaches to approximating complicated decimal values of square roots can be very important as you think more about mathematics. Well, in this lesson, we've spent a good deal of time getting comfortable with square roots. At least I hope you're more comfortable with them than you were before. Next time, we're going to talk about some related math involving raising numbers to powers other than 2. In particular, we're going to talk about what happens when you raise a number to a negative power and when you raise a number to a fraction power. I'll see you then.